Today we are going to look at an important topic in chemistry, and it is electron configuration. If you have watched our previous videos, you will have seen how we are able to demystify into the background of periodic table, the arrangement of electrons in the periodic table, the groups in the periodic table, the trend in the periodic table. Today, in furtherance of these concepts, we are going to look at this aspect of chemistry which is very important, and at the end of today's lesson you are going to learn a lot. So let's give it a go. Electron configuration. Now today I'm going to quickly take you through the structure of the modern periodic table, and before then I will quickly like to acquaint you with the learning objective for this lesson. At the end of this lesson, you should be able to 1. Define electron configuration as related to the periodic table. Number 2, you must also be able to write the electron configuration of an atom using the sublevel blocks on the periodic table, which I'm going to explain explicitly. So I would like you to pay attention. 3, at the end of this lesson, you should also be able to identify each energy sublevel in the arrangement of electron. At the end of this lesson, you should be able to explain the trend and order of arrangement of electron in the degenerate cell. And lastly, you should be able to solve problems as related to electron configuration. So let's give it a go. If you look at the electronic configuration, I'm going to show you a table that actually gives the structure of the element as they are arranged in the modern periodic table. So if you look at the modern periodic table actually is stratified into 4. Number 1, the S block. Number 2, the P block. Number 3, the D block. And number 4, the F block. Let me quickly reiterate in case you don't know or you are not aware of how these elements are arranged in each of the block. In S block, which is the first block in the modern periodic table, we have elements arranged in order of their increasing atomic number. And if you look at the screen, you will see the column containing the yellow color, which shows the arrangement, the pattern, and the stratification for the S block elements. Then if you go to your extreme left or right, extreme right, you're going to see the P block element arranged in order of increasing atomic number. Now take a look at something very important. If you look at S block element, you see 1s, you see 2s, you see 3s, you see 4s, 5s, 6s, and 7s. This is the fundamental, the bedrock of our arrangement of electron in the periodic table. So as we begin to arrange, because our goal today is to look at how we can arrange electron in degenerate shell, and we're going to arrange them in P block, in S block, P block, D block, and F block. Also, if you go to P block, you see P block is not starting from 1. Please note, a lot of students have made a lot of mistakes putting 1P. In chemistry, there is nothing like 1P block. What we have is from 2P to 3P to 4P, 5P, 6P, and 7P. This is chemistry, and this is what is generally acceptable in filling our electron on the degenerate shell. If you look at the D block element, you see from 3D, 4D, 5D, 6D, and you're going to observe that the trend from D is no longer from, there is nothing like 3p, 2d. Just like we have 1s, after 1s, if you are going to p block, you start with 2p. If you are coming back to block D block, you are starting with 3. If you are going to F block, you are starting with 4. So that's why we arrange them in that order, so that there could be a preference, and there could be a very high arrangement of this electron in the periodic table. The way they are arranged is in such that if you go from one step, you climb a higher ladder, then you enter into another degenerate shell. So for S block element, you start with 1s. For P block element, you go to 2p. For D block element, you go to 3d. And for F block element, you go to 4f. So S start with 1, P start with 2, D start with 3, and F start with 4. That is the order. Now, let's quickly look at what periodic table has to do with the arrangement of electron configuration. What is the link? And what exactly is electron configuration? Now, if you look at periodic table block, you will see that I arrange the block from S to P to D and to F. So, the electron configuration simply is the arrangement of the electron on the energy sublevel on the S, P, D, and F sublevel. The arrangement of this electron is what we call electron configuration. In other words, we are trying to configure electron based on the sublevel that such electron can occupy, and we also want to look at each of the sublevels and know how many electrons can each of these sublevel occupy. So let's go ahead. Now, if you look at this, you will see that we start with S block. The S block includes the hydrogen, the helium, and you come down to sodium, and you go to potassium. All these elements are arranged in S block, and then you observe that hydrogen and helium, both of them are elements in group 1A, and if you look at the trend, hydrogen has 1 electron while helium has 2 electrons. So they are still within the S block element. Why? Because S block can actually accommodate maximum number of 2 electrons in their habitat. So elements in the S block have their final 1 or 2 electrons in their S orbital. So S orbital can accommodate maximum number of 2. So if you have 3 elements having 3 electrons, so it means that such element will actually go to P block. You start with S block. When you are done with S block, then you extend the next electron to the P block. So now for hydrogen, if you are writing the electronic configuration, it means that it must not exceed the S block, because it has just a single electron in its outermost shell, including helium. Helium has 2. So 1s1, 1s2. So the 1s1 is for hydrogen, 1s2 is for helium. And as such, these 2 elements fundamentally, they are elements we call element in group 1A. That's the name we give them. We call them group 1A element, because they can only, the electron in their valence shell can only occupy the S orbital. So if you go from period 1, period 2, period 3, period 4, period 5, 6, and 7, regardless of the period, let me say this very emphatically, in chemistry, regardless of the period, in as much as you're working with S block, the highest number of electrons on that orbital must not exist too. If it does, it means you are no longer doing the right thing. So let's go ahead. The P block element now, the P block consists of elements in group 3A to group 8A. I have taken time to show you how we grouped the periodic table, and this actually serves the fundamental purpose of giving us the clue as to how the periodic table is arranged. So there are 6 p block elements in each period. In every period of the periodic table, there are 6 p block elements in each periodic table, and because 3p orbital can hold up to 6 electrons. Remember, s orbital can actually hold up to 2 electrons in the periodic table, while p block orbital or p orbital can hold maximum number of 6 electrons in the periodic table. So if you are 6 maximum of electron in the atom of any element in the periodic table. So as you begin to go from the first element to the second to the third to the fourth to the fifth, you are going to see that once the s block orbital is completely filled with maximum number of 2 electrons, what you need doing is to move the next electron into the p block element. I'm going to show you how this is done. We are going to take the first 30 elements from the periodic table and we are going to do justice to their electron configuration, starting from hydrogen, helium, lithium, beryllium, boron, carbon, nitrogen, oxygen, fluorine, neon, sodium, magnesium, aluminum, silicon, phosphorus, sulfur, chlorine, argon, potassium, and calcium. And we are going to go from scandium, titanium, vanadium, chromium, manganese, iron. We're going to look at the nickel, the copper, the zinc. We are going to look at these first 30 elements in the periodic table and look at their electron configuration. Now, coming to D block, the D block contains transition elements. This has been emphasized over time. The D sublevel are 1 less than the period number, like n minus 1. That is the general formula given to this D block element. Please note this, because by the time we begin to explore further, looking at the electronic configuration of the transition elements, starting from scandium, titanium, vanadium, and the rest of the elements in that block, you are going to see that the D sublevel has 1 minus 1 less than the period number. So regardless of their period now, we just take 1 out of their period and that will form the basis of their own electron configuration. Please, it's very important. In other words, if you are arranging the electron of any atom in the S, P, and D subcell, you need to start from S. Once S has or is able to hold up to 2, you move to the P block. Then P block can hold up to 6 maximum number of electrons. When that is done, you move to D block, and then D can hold up to 10 electrons. In fact, I'm going to show you how this electron can be arranged on the S, P, and D, and even F subcell or orbitals, and how this is done for the first 30 elements. But you need to have the understanding of the basis. This is the bedrock, this is the foundation, and I'm trying to lay the foundation so that you understand further how chemical synthesis and electron configuration is done. Because if you look at past questions, you will have seen in different years, there is no how questions will not come out in electron configuration. So it's important that you pay attention and you watch this video to the end. Now, like I said, D block contains 10 maximum number of electrons in its orbital. So if you are working with, take for instance, you're working with carbon, the atomic number of carbon is 6. So if you want to start the electronic configuration of carbon, you need to start from the S. When you're done with the S orbital, go to P orbital. When you're done, you come back to D orbital. So I have seen students over the years writing electronic configuration of any element and then starting from P or starting from D block. No, it's wrong. The right thing is to go sequentially from the S block to the P block and then to the D block element. going from one period to another. So S can hold maximum number of 2 electrons, P can hold maximum number of 6 electrons, D can hold maximum number of 10 electrons. So let's go to F, which is the last block in the periodic table. If you look at it, the F block contains inner transition elements and 2 rows at the bottom. If you look at the modern periodic table, you understand that the F block element, which you call the lanthanide and the antennae, they were separated. They are separated from the major group. So they brought them down in order to stratify them and to show that they are F block elements. So the F block element contains the inner transition element, 2 rows at the bottom of the periodic table, and the F sublevel. Now, you know, we said D is 1 less than their periodic number. Please, all these things are very important. I'm laying emphasis on this so that you can understand and you will not have problem when you are solving any question on arrangement of electron, or what we call electron configuration. So we say that in D block, the number of electrons in the arrangement actually is less than 1. Less than 1, considering their period, the number of period, or their period number. Now come to F block element. When you come to F block element, you understand that instead of 1, F block element, their sublevel is 2 less than the period number. So there are 14 elements in each F block, because there are about 14 electrons in their orbital. So 14 electrons in F block orbital, 10 electrons in D block orbital, 6 electrons in P block orbital, and maximum of number of 2 electrons in S orbital. So let's look at the electron configuration using the periodic table. Now we want to use the periodic table as the basis of our arrangement. Now when you look at the metal, the alkaline earth metal, the metalloid, the non-metals, the noble gases, if you look at it and look at the trend, let's start from the first period. The first period, the electron or the element in the first period is hydrogen. Hydrogen has only 1 electron, because hydrogen has 1 atomic number. So because it has only 1 electron, we just have hydrogen to be 1s1. However, if you go to helium, you have 1s2. Now if you now go leave period 1, come to period 2. Now period 2 now has first 2s and 2p. So period 1 has only 1s, period 2 has 2s and 2p, period 3 has 3s and 3p, and we're going to follow that order. Now if you look at the period 2, you see 2p block. It means that any electron that must fit into that configuration must actually have its electron coming out from the S block, coming into the P block. For instance, if you look at beryllium, hydrogen, helium, lithium, beryllium. Beryllium has atomic number 4. So if you want to write the electronic configuration of beryllium, you start from 1s1, 1s2. Now you cannot say 1s3. Why? Because S orbital can only accommodate maximum number of 2 electrons. So you go to 2p. You now say 1s1, 2s2, then 2p1, 2p2. Now look at what you are seeing on the screen. You see 2s2, 2p6. That means any electron configuration of any element that will have this electron configuration actually must be an element with 8 atomic number. So oxygen has 8 atomic number. So the period 2, we can fit in 2s2, 2p6 for oxygen. Don't forget, before the end of this video, you are going to see, I'm going to personally construct for you the electronic configuration of at least the first 20 to 30 element in the periodic table. So it's important that you follow to the end of this video. Now coming to period 3, you see the 3p block. Now we are graduating from 1s to 2p to 3s and 3p. It means that once the s is filled up, we move to p. Once p is filled up, we move to d. So now you remember, we only have s block for the first period. For the second period, we have s and p. For the third period, we have both s and p. So let's go ahead. Now, if you want to write the electronic configuration, let me give you a comprehensive guide. This comprehensive guide will help you regardless of which element you are considering, regardless of the electronic configuration of any element whatsoever. If you follow this guide, it's going to help you and guide you into doing the right thing across the period and down the group when you are writing electronic configuration. So the first instruction, the first guide is you must locate the element on the periodic table. That is why it's important that you know the position of the element in the periodic table. At least for SSCE, you are required to know at least the first 30 elements, from hydrogen, helium, lithium, beryllium, boron, carbon, nitrogen, oxygen, fluorine, neon, sodium, magnesium, aluminum, silicon, phosphorus, sulfur, chlorine, argon, potassium, calcium. That's the first 20. When you are done, you must be able to position them on the periodic table. Then you go to the D block elements, starting from the first row, the scandium, titanium, vanadium, chromium, manganese, iron. You need to go through and look at them sequentially. This will help you to be able to construct the electron configuration, because if you don't know their position, you will not know the atomic number. If you don't know the atomic number, there is no how you can play around electron configuration. So the fundamental is that you know the atomic number and their position, how they are located both in the period and down the group in the modern periodic table. So when this is done, then you can go to step 2. Step 2, you write the field sublevels in order going across each period. There must be an order. I'm going to show you before the end of this video the order, the pattern with which we use in arranging this. We don't just scatter electron anyhow all around the orbiter. Each orbiter has capacity, so we need to work based on the capacity of S block, P block, D block, and F block. So if you exceed the total number of electrons that must contain in each orbiter, then you are no longer doing electron configuration, you are doing something else. So for you to be able to do this, you need to watch this video and then follow this guide I'm giving you. These guides are the bedrock upon which you can build your knowledge, and then you can be able to write electron configuration properly. Number 3, after you have examined the fields sublevel in order of their period and the group, 3, you complete the configuration by counting the electron. We do 1, 2, 3. We do arithmetic in chemistry. So we need to follow the sequential order. So complete the electron, the configuration by counting the electron in the last occupied sublevel block. I will need to repeat this and emphasize it very clearly. In the last occupied sublevel block, I'm going to show you how this is done. When and if you follow these important guides, it will help you to write a well-constructed electron configuration. Now let's look at one problem. Let's see if we'll be able to solve this problem using the guide. Using the sublevel block on the periodic table to write the electron configuration for chlorine. Now, if you just come across this element called chlorine, you don't know the atomic number, you don't know the position in the periodic table, you don't know which period, you don't know which group, you cannot solve this problem. You cannot. So the fundamental, the basis is for you to know which element is chlorine. Now you agree with me that if we look at the periodic table, chlorine has atomic number 17. Knowing this has solved half of the problem. And then you also need to know the group and the period. So the group, chlorine belongs to group 7A, and then it belongs to group 3 in the periodic table. So having this fundamental information about chlorine will automatically help you with the use of the guide I gave you to solve this problem. So if you don't know the atomic number, you don't know the group, you don't know the period, you can't solve this problem. So look at the problem now. Now we have actually been able to extract certain information that is very important for further chemical analysis in writing electron configuration of this particular element. So let's do justice to it. Use the sublevel block on the periodic table to write the electron configuration for chlorine. Now, look at it now. Write the field sublevel in order, going across each period. Now, in period 1, you have 1s, which actually is for helium. You have 1s2. Now, go to period 2, you have lithium. That will be 1s2 and 2s1. Now, going from lithium, you go to beryllium, you go to boron, you go to carbon, you go to nitrogen, you go to oxygen, you go to fluorine, and the likes. When you follow this trend, you will be able to do justice to the filling of this orbital with the appropriate number of electrons required to be in each of the sublevel. So if you look at period 3, you will see from sodium to magnesium. Now look at it. From period 1, we have 1s2 maximum. So once you reach 1s2 in period 1, go to period 2. Now you now start from 2s, because you are now in period 2. 2s1, 2s2. After succeeding in having 2 electrons in the p orbital, go to 2p. Having 2 in 2s, go to 2p. And you know, like I have explained earlier, p can accommodate maximum number of 6 electrons. So you start from 2s1, 2s2, 2s2, 2p1, 2s2, 2p2, 2s2, 2p3, 2p4, 2p5, 2p6. That is sequential. It's very sequential. You need to follow the order. Then you go to the next period. Period 3, you have 3s, then 3p, 3d, and you follow that order from the first element to the last element. So in period 1, you have from hydrogen to helium. Please don't make mistake. Don't make mistake. In period 1, we only have from hydrogen to helium. In period 2, we have from lithium to neon. From period 3, we have from sodium to magnesium. At least considering the first 20 elements in the periodic table. Let's go ahead. Now, so using the sublevel block on the periodic table to write the electron configuration for chlorine, we have considered step 1, step 2. This is step 3. We want to complete by counting the electron in the last occupied sublevel. So if we look at it, 1s2, 2s2, 2p6, 3s2. That is the one preceding the 3p5. So we need to count from there. 1s2, that means 2 electrons. 2s2, that's 2 electrons. 2 plus 2 is 4. 2p6, that's 6 electrons. 4 plus 6 is 10. Then 3s2, 10 plus 2 is 12. That means 17. Remember, we got the atomic number for chlorine. 17 minus 12 will give us 5. So what we need to do is just write 3p and put the 5. That is how it is done. So we have followed step 1, we have followed step 2, we have also followed step 3 sequentially in order to solve a problem on electron configuration. So if you look at period 4, the 4s sublevel filled before the 3 sublevel because the electron in the 4s sublevel are slightly lower in energy than those in 3d sublevel. This is very important. Please pay attention to this. If you look at 4s sublevel and 3d sublevel, there is a synergy, a kind of a regulation, hybridization between this 4x level energy and 3d. So there's a slightly lower energy of that of 4s than that of 3d. So 4s will come before 3d. Instead of 3d coming before 4s, 4s will come before 3d. This is chemistry, and this is what is obtainable. If you do anything outside this principle, you cannot actually do the right thing. This order occurs again in period 5. When you fill the 5s, you fill it before filling the 4d sublevel, and in period 6 too, you fill the 6s before you go to 5d. So this is the order, and this is the sequence. And if you look at this now, you are going to see the electronic configuration of potassium, calcium, scandium, titanium, vanadium, chromium, manganese, iron, cobalt, nickel, copper, and zinc. This is from 19 to 30 element, from 19 to 30 in the periodic table. And you see the atomic number first. You need to know their block. The first one, which is K and Ca, which is potassium and calcium, actually they are in 4s block. Then from scandium to zinc, they are in 3d block, because they are all transition elements. So until you understand this, you may not be able to do their electronic configuration. Now, do you also know that we can do abbreviation in writing electronic configuration? Yes, we can do abbreviation, but this abbreviation must follow a kind of a protocol, because if you fail to follow the condensed protocol, you may not be able to get the electronic configuration. Now, argon is a noble gas, and it has its shell orbital completely filled with electron. Argon has atomic number 18. So if you want to write the electron configuration of potassium in abbreviation form, in the condensed form, you put argon, then bracket, how many electrons remaining? 1, because 19 minus 18 is 1. So you put your 4s 1. Why do you put 4s? You only put 4s because potassium is in 4s block. Can I say this again? Potassium and calcium, they are in 4s block. So after you have condensed the previous electronic configuration, instead of writing a sequential and writing a long term or long form, just put your argon in a condensed form, put it in bracket, then add the remaining number of electrons based on the block of these elements. So you can follow this sequential order to write for scandium, for titanium, for vanadium, for chromium, for manganese, for iron, for cobalt, for nickel, for copper, and also for zinc. So the same thing if you go to period 4 and you look at the 4p block. So you need to also write in condensed form so that you can be able to actually save some time and save some energy, especially when you are doing objective lesson. You don't have to write all through. Write in condensed form. You write your answer, then you get your answer right. So some exception in sublevel block order. Now, let me round up this section by telling you that there are some exceptions. These exceptions are very paramount that you know them, because if you don't, you'll be committing a lot of errors when you are writing electron configuration. Of course, there's a general pattern, there's a general rule, there are guides, but in some specific element, there are exceptions. In filling the 3D sublevel, exception occur for chromium and copper. Now, in case of when you are writing and you come before 4s and 3d, I told you 4s supposed to have maximum number of 2, 3d supposed to have maximum number of 10. So instead of filling one completely and filling one half completely, so you fill all half, you fill all the orbital halfway. You just put one electron in their orbital. I'm going to show you 3 important rules that governs the electron configuration. If you don't know these 3 rules, you cannot actually be able to explore when it comes to electronic configuration. So some exception are in sublevel block order. I've told you of copper and I've told you of chromium. So it's the same thing. You need to follow the trend. Is either 4s and 3d are half filled, or 4s completely filled and 3d is half filled, or 4s is half filled while 3d is completely filled. So you take one, you use one, either 4s is completely filled and 3d is half filled, or 3d is completely filled and 4s is half filled. You have to follow the sequential order. So if you learn and you go through the electronic configuration, you are going to see that this actually is applicable in most of the problems that will be coming across. So if you use the periodic table to give the symbol of the element with each of the following electron configuration. So you can also be asked, they will write the electronic configuration for you. They will ask you to actually name the element. What you need to do is very simple. Go to the electronic configuration, count the number of electrons in s, p, d and f orbital. When you know the total number, then that total number will give you the element that its electronic configuration is written. So you can see for cobalt and you can also see for bromine even on the screen. We have come to the end of module 1 of this lesson. I will want you to watch the next video, module 2, which is the complete part of this teaching. Let's go to the exam guide and see some few questions that we can quickly solve and see how we can actually address questions related to periodic table and electron configuration. Question 1. The ionization energy is affected by the following factor except 1. Distance of the outermost electron from the nucleus. B. Size of the positive nuclear charge. C. Screening effect of the inert electron. D. Ability to attract shared electron. If you look at all these parameters, they are asking us all of the following affect ionization energy except 1. So you look at it that the distance of the outermost electron from the nucleus actually is a big factor when you come to ionization energy. The size of the positive nuclear charge actually does not matter, but the screening effect of the inner electron matters. The ability to attract shared electron also is not a factor. So if you look at the 4 options, the best answer here is the ability to attract shared electron. It's not actually related to ionization energy, because ionization energy tends to give you the ability, the capacity of the atom of an electron to give away, not to attract. It's giving away. It's ionizing. So attracting electron here is wrong. So that would be option D is the right answer. Go to the next question. The presence of unpaired electron in an atom of D block element account for its ductility, its lustrity, its malleability, and its paramagnetism. Actually, it is for its paramagnetism. That is the presence of unpaired electron in an atom of a D block element. In question 3, which of the following gases is used to retard the vaporization of the filament in a light bulb? Actually, if you look at oxygen, they are asking you the gas that actually can be used to retard vaporization of the filament in the light bulb, giving us options of oxygen, hydrogen, argon, and helium. Argon actually is a noble gas. Helium is a noble gas. Hydrogen actually belongs to group 1, while oxygen is having atomic number 8. So in this option, hydrogen actually is correct because it retards the vaporization. Now going to the next question. Element with ionization energy would A. have effective nuclear charge, B. lose electron easily, C. have large atomic radii, D. have low atomic number. Actually, if you look at the options, you see that it will have a very high effective nuclear charge. Number 2, it can lose electron easily. Number 3, it have large atomic radii, and 4, have low atomic number. So have low atomic number is the correct answer. So having low atomic number is obsolete among the options provided. Last question. An element Y has the electronic configuration of 1s2, 2s2, 2p6, 3s2, and 3p4. To what period does it belong in the periodic table? They are asking for the period of this particular element. Now look at the electronic configuration again. 1s2, 2s2, so 2 plus 2, 4, plus 6, 10, plus 2, 12, plus 4, that is 16. So that is sulfur. So which period does sulfur belong to in the periodic table? Actually, it belongs to period 3. So A is the answer. That will be the end of our lesson. I will urge you to subscribe to our YouTube channel so that you can watch our subsequent videos. Till then, I remain your chemistry instructor.